All right, everyone, welcome back to lab. So today we're going to be playing with what's known as Faraday's law. I'll talk about that in another video, the more introductory video, but this one is simply about the actual experimental apparatus that we're going to be playing with. So in the first part, we are going to have a power supply and what's known as a galvanometer. So galvanometer is simply something that measures the current. So on here, you can see this thing is going to measure current. So in the first part, all we basically want to do is figure out what direction is the current going through this object. So this is actually part A. So I'm going to turn this thing on, just put some sort of potential across here. It doesn't matter how much. I'm going to go 9 volts for now. Now notice that initially there's currents running through here, but the galvanometer is not moving. So to get it to actually detect the current, I have to use one of these 3 buttons. So basically each one of these buttons corresponds to a different scale at which you're actually measuring then the current. So to actually do a measurement of the current, you then have to hit one of the buttons. So in this case, it gets deflected to the left. I hit this one also to the left, this one not as much to the left. So for this lab, we're going to use button number 1 here, which is then going to be the smallest scale so we can see the biggest amount of deflection. So the first part, you're just basically going to see, okay, so if the current is going through this in one direction, I get a deflection in this direction. But if I change the polarity of the battery, if I switch the direction of the wires here, and I do it again, this thing is now going to deflect in the opposite direction. So from here, you're basically just trying to understand what direction the current is going through here versus the direction of deflection. This will be important for the other parts of the lab. So that's the first part. That's part A. Part B then is just figuring out what side of this is the north side and what side of this is the south side. This is just a regular bar magnet. This was in your kits that we used this last week. So to do that, as the lab manual says, basically all we're going to do is use our compass that we used last week. So here's my compass. And I'm simply going to move this guy near here. Now, what will happen then is remember that the south side of the compass is attracted to the North Pole. So what I should have then is that the North Pole of the compass is pointing away from the North Pole of the magnet, which means that this side that's down is actually the north side. So if I switch it over, what happens in that case then is the north side is attracted to it because this is the south side. So north side, south side. So once I know which side is the south side, which side is the north side, put a piece of tape or marking on here or something that tells you that this is the north side. So take a pencil, put a little dot on there or a pen or something along those lines. That way we know which side is which. Good, so that is part B. Now part C, what you're gonna be doing then is making predictions on what direction your needle here is going to deflect based on the direction at which the compass is moving and what side is actually moving into it. So to do this, we're going to construct a simple circuit. So in this case, we're going to take our coil. So this is a coil. Connect alligator clips to this guy. So here's my alligator clips. And I'm going to put one wire from one side. I'm going to plug that into the galvanometer. And then I'm going to connect another wire to the other side and connect this guy also to the galvanometer. Okay. Now, what the lab basically wants you to do is flip this guy on the side. And what you're going to do is, I have to do this left-handed so you can actually see, I'm simply going to move the magnet inside of the coil and then pull it back out. So each one of these is going to correspond to a different prediction. So here, what you want to do is make a prediction on if this is the north side going in, what direction should the currents go based off of the induced magnetic field, which is going to happen inside of the wire. Predict then what direction the current should be going, which is then going to be determined by the direction of deflection of then the galvanometer meter. Then when I pull that out the other direction, make a prediction of which way it's going to go in that direction, which will then correspond to a direction here, and then basically fill out the sheet on what is then going to be your predicted model. And then you're actually going to do the experiments then to verify what it is that you got and then understand basically why that is. So here you're going to do it first going in with the north side, going out with the north side, flip it over, and then going in with the south side and then out with the south side and make predictions on the direction of the galvanometer deflection based off of the induced magnetic field, which is happening on the inside. So to do this, you're basically going to have to do 2 things simultaneously. So here to see the deflection, I'm going to have to push and hold 1. Now note, the bigger the deflection will become will happen when you move the magnets faster. So here I'm not pushing the button, so I'm not seeing any deflection. But now if I hold the button and I do this, I'm going to see a deflection. Okay. So in this case, when I pull it out, it deflects to the left. When I go in, it deflects to the right. So this is Faraday's law. So Faraday's law, again, is just simply saying that I'm creating a magnetic field inside of the coil, which actually means I'm creating a potential difference inside of the coil, which is what's known as the induced EMF, which is then causing current to move through the wire based on the fact that there's now a potential difference. Okay. So this is all we're doing then in part B. So in part B then, actually no, it's part C, sorry. In part C then you're making that prediction. Now finally, part D has to go back to, now we're gonna keep this guy connected to him. So I'm gonna leave this guy alone. Now I'm gonna take a secondary coil, here's my secondary coil, and now I'm gonna connect this guy to the battery. So we run one portion out here. Let's put an alligator clip on this side. I'm gonna connect this guy over here. Wood. Another alligator clip on this side. Connect this guy now back into the battery. Now, what'll happen here is, one thing you'll notice is, if I, again, push and hold this button, let me turn this on. Actually, I need a switch, but I'll do it this way and that'll be fine. So I'm gonna put these guys right next to each other. So what I want is the axis of this one inside of the axis of him. So when I turn this guy on, you'll see a deflection. If I turn it off, you'll see another deflection. So let me kind of turn up the potential here. So in that case, when it turns on, it deflects one way, turns off, it deflects the other way. Turn on, deflects one way, turn off, deflects the other way. Here, you're actually not gonna be turning this on and off. You'll use the switch. I just kind of forgot to grab the switch. So you'll have to put a switch into here. But basically what will happen is, another thing you'll notice is if I hold this and you watch the needle, after I turn it on, it deflects quickly, but then it stops. It doesn't move anymore. So what happens is the induced EMF, which is happening inside of this guy, will only be induced while this one has a changing magnetic field. So once this thing reaches its maximum current, the magnetic field inside of him is non-zero, which I can actually show by taking this, not actually touching it. This guy is actually deflecting because I have a north side here and a north side here. So this is actually being pushed over. Or if I put this guy here, it'll get sucked inside of it. Okay. So basically this guy's going to create a magnetic field. That magnetic field will actually be a steady magnetic field. That steady magnetic field then won't induce an EMF inside of him. So this is only happening when a switch is being opened and closed, or when the power supply is being turned on or turned off. So here we're actually going to put in a switch on the inside. So you'll close the switch, cause the current to move, open the switch, cause it to stop. Again, with some sort of potential, which is acting on here the entire time. So you'll have to turn up the potential a little bit to kind of see a better deflection in this case. But that's basically part D. And then the last thing you're going to do is take a semicircular or semi-cylindrical piece of metal. So basically it's a cylinder, it's kind of cut in half. You'll put that on the inside, close the switch, and basically watch what happens. Okay. So ultimately, all you're going to be doing then is making your predictions. You're going to fill out that chart with your predictions. You'll do it experimentally to basically verify that what you get experimentally matches that what you do in the theory. So in the other video, we talked about the theory behind it. So you use that to compare and determine the direction of the induced magnetic field as a result of the magnetic field of the exterior magnet, which in this case will be the bar magnets, and how that guy is moving and how it's actually changing. So that's this lab. So again, this is the experimental setup. So in the first part, all you're doing is, again, connecting this guy directly to the galvanometer. Again, determining the direction that the needle is going to move based off the direction at which the current is moving through the galvanometer. So in here, this is the negative side, this is the plus side. Again, depending on how this thing is actually set up. Second part, again, all we want to do is determine the direction of the magnetic field. And the north side points away from the north side. So in this case, this is the north side. I'm going to make some sort of marking on there. Second part is only dealing with this portion. Again, you're going to have the magnets moving in and out. And then you're measuring the deflection, how this guy deflects. And that's going to determine the direction of the current. And then finally for part D, you're using the 2 coils, using both of these guys simultaneously. This one will be the exterior magnetic field, and then this one will be the induced magnetic field. So again, your predictions are always typically going to be about the induced magnetic field. So that's it. So nice and easy. So it's all about just making your predictions and then verifying those predictions.